Welcome to Hitex and to today's webinar, Debugging and Tracing for NXP's S32K Arm Cortex M7 MCU with UDE. Our appointment today is again with an old friend and welcome guest here with us, Jens Braunes from PLS. He's product marketing manager at PLS Development Tools. He joined the company in 2005 as a development engineer. He worked as software architect and was actively involved in the design of PLS's innovative test and development tools. In the last years, he focused on tool support for on-chip emulators and trace. In 2016, he expanded his activities to the areas of product management and technical marketing.
Welcome to this webinar. Today, we will take a look at the debugging and the tracing capabilities of UDE for a ARM Cortex-based microcontroller, which is the S32K microcontroller family from NXP. I will give you at first getting started. So as Wolfgang said, and I show you the basic debugger functions. And then in the second part, we will also go through the topic of tracing, and I show you how to prepare the debugger and also the device for capturing program traces for doing some runtime analysis and also for code coverage. Okay, then let's start with a short overview about the S32K family. The S32K is a whole family of automotive-grade microcontrollers that are all based on Arm Cortex-M, which is the core architecture. Relying on that, the devices offer scalability, high performance, and also low power consumption. The MCUs of the S32K family are part of the so-called S32 automotive processing platform. So it's only a part of this. So there are other devices available based on also on Cortex R and Cortex A. The S32K devices are designed or used in body control and zone control and also in electrification applications. So everything automotive. And also very interesting, they provide functional safety and also embedded security, for example, in compliance to the ISO 26262, and they achieve ASIL B or ASIL D. The family is divided into three performance categories. So we have the K1, which is a single core device, or the K1s are single core devices based on Cortex M4 and Cortex M0 Plus. Then there are a lot of devices based on Cortex M7. This is the S32K3 series. Here we have single core configurations, we have multi-core configurations, and also lockstep configurations. And the latest addition to the family is the quite new S32K5, which expands the series to higher performance by adding a Cortex R52 core together with the M7 cores. In the session today, I use a device from the S32K3 series, which is the S32K388, which is a quad-core Cortex M7 microcontroller, which can be configured either as a quad-core M7 MCU with one lockstep core. So there is a permanent lockstep core here. In this configuration, we can use 4 application cores, and then we can also configure the device by the application to have 2 lockstep cores plus 1 non-lockstep core. So that means that you have then only 3 application cores available. If you look at this picture here, you see also that we have a security core, which is called the HSE security engine that provides encryption, secure boot, and so on. The firmware of that core here or that module comes from NXP and cannot be accessed by or somehow closed. So the core cannot be accessed by the debugger at all, and so you will not see that HSE core here in the debugger later on. The hardware functions for the debugging and also for tracing are all based on Arm CoreSight, which is the debug and trace technology from Arm. That means that the debugger can connect it either using a JTAG or a SWD to the device. And we are using standardized connectors, which we have on all the evaluation boards that are available. And for the debug tool, the CoreSight subsystem provides hardware breakpoints, triggers, and so on. And that is very useful for the basic debugging functions like breaking and single stepping, of course. And the triggers allows also a synchronization of the debug actions across the cores. That is very interesting for us. Later on, I will show you this on an example. Before I switch to the debugger, to the UDE, a few words about the hardware setup. This is an example picture. You see the NXP evaluation board with the this small part is the S32K 388 microcontroller. This picture shows the simplest hardware setup for debugging. We see the UDE 2 Pro, which is the basic debug device of our universal access device family, connected to the PC via USB and to the microcontroller using a we call it a JTAG SWD adapter. This is ARM specific here. It's not quite good, that picture here. This is the adapter here, which is the only target specific part here in that setup. You can also use the UDE 2 Pro and all the other devices from our access device family for other architectures like the Ulrix or RH850 or something like that. What you need is an appropriate debugger license and of course the matching adapter for the specific evaluation board. Since this webinar also covers the trace functions for the S32K, the actual hardware setup on my desk looks a little bit different. Instead of the UDE 2 Pro, I use the UDE 2 Next. The reason for that is that the UDE 2 Pro provides only basic debugging functions and has no trace memory and does not support external trace interfaces. You can use this device for on-chip trace. That means if you can record the trace information on-chip in an on-chip trace buffer, but this is quite small on these devices. We have only 4K for that. And with the UDE 2 Next, we have 512 megabyte for storing the trace information. But more details later. I use a demo application which is compiled and linked for flash memory. So you need to program it into the flash. And I use all the 4 cores here in the configuration or in the application. And so I do not use any lockstep configuration here in order to have all the 4 cores available. Then let's quickly jump to UDE. I have already opened UDE and The first I'd like to show is how to create a new debug session. We call this workspace. So we have on the right side some buttons here for opening workspaces and also for creating one. And on the left side we can open already existing workspaces here. So we create a new one. I press new workspace. And then we need to type in a file name for that. Okay, it's already there, so I reuse that here. Click open. And then we need to tell the UDE which target we want to connect and which debug interface we want to use. And for that, we have a so-called target configuration, which is basically a file. You can browse in the file, of course. If there are any available, then you get a list of that. But right now, this list is empty and we need to create a new one. The simplest way is to use our default target configurations. And you see we have a huge list of all the supported microcontroller architectures. And here we can look in that list for the specific board that we have, or we can type in the name of the microcontroller, for example, the S32K 388, and then look for the target configuration file for that specific device. So we have two of them. One is for the lockstep configuration and another one without lockstep configuration. I take this, press finish, we save it on the computer, and then I can press OK. Then UDE asks for the cores that we want to see in the debugger session. So default is we want to see all the 4 Cortex M7 cores. So I leave the checkboxes untouched. You don't see the HSE because it is not accessible by the debugger. And once I have made my decision, I can press OK. And UDE now connects to the device. At first, we need to load our target application that we want to troubleshoot and want to test using the file menu, load program, and then I select the ELF file for that. So ELF file or hex file, both are possible. I use the ELF file, which contains also the binaries and not only the debug information. Press OK, and then we get this window opened. And here we see our file and then some checkboxes and also some cores here. In UDE, all the cores are represented by a so-called core debugger. So we have 4 core debuggers available for the 4 cores on our device. You will see later on that also all the windows belonging to a specific core are colored by a core color. So we have them already here. And you see that on the standard connection, the core 0 is in reset and the other cores are inactive. And for that reason, we need to use core 0 to flash the application. To control that, we have these blue checkboxes here. That means handling the binary. Core 0 is the only active one, so we tick this checkbox. It is checked by default. And we want to load the debug information to all the other cores as well, because we want to debug all the cores and want to see all the functions, all the variables, and so on. And for that, we have the green checkboxes, which controls how to which debug information is loaded to which cores. So we leave that also untouched, press OK, and then UDE tries to load all the binaries to the device and all the debug information into the debugger and asks for a file name. this is not, it happens not in all cases that we need to browse in some file names because the ELF file contains the information where the source files are located on the computer, but sometimes you copy the project to a different location or to a different PC, and then the information in the ELF file does not match the actual situation on your computer. And this is the case here. So UDE asks for the first source file that should be displayed in the debugger, which is the startup code here. But we want to tell UDE how to find the all the other source files. For that reason, I skip this, press cancel, and then the Flash tool gets opened, and we can program the binary to the device, which is quite fast. I close this, and then we want to show or want to access our source files. And for that, I go to the config menu. There is a debug server configuration, which allows us to do a lot of settings here. And one of these settings are the source file handling. We have two buttons here. The path management allows you to define replacement rules for the path information from the ELF file, and we have an alias button, which I open now, and we see here a alias or a information for the skipped startup code here, and to make this, to allow UDE to open this file again, I remove this setting here. Okay, then I go to path management and define some replacement rules. So we look into the ELF file information. So we have two file folders here where the where we have the source files, and for both I define a replacement rule by browsing my computer for the folders, okay, and for the second folder, for the board folder as well. And once we have done this step, then we can close this window. And if we press, for example, the Show IP button here in the toolbar, then the startup code is automatically, or the source file for the startup code is automatically opened. So then we can start the application, and we want to see something. And for that, I open also the watch window from the Views menu, and we browse in some variables. For example, these variables here, put it on the right side, for example, and then I enable the so-called periodic refresh, which allows us to have a real-time view of all the variables here. Okay, so we see we have variables or counters or idle counters and worker counters for each core. So we see all the cores are running. We can see this also here on the core indicators on the toolbar. And then we can start debugging. For example, we can set a breakpoint maybe on core 2. Maybe we can open the function updates of seconds. So we can set a breakpoint here by pressing or by clicking on some of these blue points here. For example, we set a breakpoint here. I open also the breakpoint window, which provides the list of all the breakpoints. And then we can also look at the core stack. So, and also the locals of our function here. And we can go through the core stack, see what was the caller of this update function here, what are the locals at this core stack level here. And then we can also open another source file, for example, for the core 0. I highlight or I click on the core 0 here. Then the core 0 is the active one. Then I can click on the show IP button here, and then I see, okay, we are at this breakpoint here, and we synchronously stopped also the core 0. And if you look at the core indicators here, we have stopped synchronously all the other cores. And then I can, for example, do some single steps here, and we see that with the single stepping on the core 2, we do some steppings as well in the other cores. This is the debug synchronization that is realized using the CoreSight triggers that I mentioned before. Okay, this debug synchronization is enabled by default, but you can of course change this synchronization if, for example, if you want to debug some independent applications that are running on the several cores here, and you want not influencing a specific core and want only focus on core 0 or something like that. For that, we go to the config menu, and we have the multi-core run control configuration that provides us a group of synchronized cores, and we can, for example, break this group by removing core 2. And then if I start, for example, the core 1, I enable core 1 again, core 0 again, and then I press the go button, then you see that all cores except of core 2 are running right now. We can see it also very well in the watch window. I can then separately start core 2 by activating core 2, pressing the go button. Then all cores are running. If I enable the breakpoint again and stop in core 2, the other cores are not influenced by this breakpoint here. If I want to change this behavior to the default and bring the core 2 back to my run control group, I have to break all the cores. So core 2 is already stopped. For the other cores, I do it by manually breaking. So I select one of these 3 cores and press the break button. Now all the cores are halted. I go to the run control management and add the core 2, and then I can disable the breakpoint, start the application, and once I enable the breakpoint again, all the cores are stopped again. Okay, this is standard debug functionality for multi-core systems like the S32K with in multi-core configurations. Another nice feature in UDE for doing multi-core debugging is dealing with shared code. So in a lot of applications, you have library functions or some functions that are executed by all the cores, and you don't know which core is actually the core which executes a certain function. For that, I have prepared a workspace which uses the same application but has some other windows opened. So the same application, I don't need to flash it because it's already flashed. So I only need to verify that the flash contents is the same that I want to have. And then we have the same application, same watches, but I have opened another code window or source code window, which shows us a function here, which is executed by all the cores. And the function is on all windows the same. We can look at the machine code with the which shows us also the addresses. Here we can look at the addresses. Okay, for the core 0, we have this address, and this is just the same address as we have on the core 1. But if we start the application, of course, if you set a breakpoint here in core 0 and do some goes, and I'm sure that all the cores executing that function, only core 0 hits the breakpoint. The others would not stop at all. And the reason for that is that the breakpoint is always core specific. You can now set a breakpoint for the other cores as well. It is maybe okay for 2 cores or even for 4 cores. But if you have more cores in your device, then it would be very annoying to set the breakpoint for all the cores. For that reason, remove that. We have multi-core breakpoints in UDE. These multi-core breakpoints can be set, for example, from the source code window by using the context menu and insert a multi-core breakpoint, or you can change a single core breakpoint in the breakpoints window by using the breakpoint edit function and tick this checkbox here, multi-core, to make it a multi-core breakpoint. And then you see the symbol has changed slightly, and also the symbol is now visible on all the other windows here. And if we look at the breakpoints window, then we see that we have a multi-core breakpoint, which is in fact technically spoken a single core breakpoint that is set for all the cores of a run control group. And if I do the stepping or the go again, then we see, okay, now we hit the breakpoint in core 2, here, the yellow one, do another step or another go, then we are on core 0 again, and then we, okay, it's not deterministic, this behavior here, or sometimes we should hit the breakpoint also here, right now in core 1, and so on. And this is a very helpful feature if you have shared code in your multi-core application. Okay, time is running, so I'd like to switch from stop mode debugging using breakpointing, single stepping, and so on to tracing. So tracing, you may know, is especially useful for debugging if you can't do stop mode debugging anymore because of you have parallel execution, you have some timing issues in your application, and whenever you break the application, you want get an inconsistent state, or the issue that you want to observe is hidden by your break. So tracing is then very useful if you have a negative impact on the application's behavior in stop mode debugging. Also, you get very detailed information about the runtime behavior of your application using tracing. You can create, for example, profiles. You can reconstruct the core graph of your application. You can measuring, for example, code coverage, which is not a debugging topic. It's more or less a testing topic. You can also visualize task execution if you have an operating system in place, and a lot of useful things related to runtime and analyzing of the application as well. So in the S32K, we have also the CoreSight subsystem for tracing. That means we have a embedded trace macro cell, the ETM for program tracing. We have an instrumentation macro cell for instrumentation tracing here for each core. So instrumentation trace means that you do a kind of printf debugging. However, instead of using a printf function in your application, which has a lot of overhead, the application uses special instructions to write an application value to a so-called stimulus port, and these values are then output into the trace stream, with very low latencies and also with low overhead. This is not the topic for today. I'd like to use the program trace of the ETM in the next few minutes. The recorded trace information can either be stored in an on-chip trace buffer, so it's called ETB, or it can be transferred off-chip using a parallel trace interface. So the ATB is rather small, so 4K, that results in very short trace runs. With the external trace option, for example, using our UAD2 Next, you get much longer traces. So in the UAD2 Next, we have, for example, 512 megabyte trace memory, and that is quite enough for most use cases. If you want to use the external trace option, you need a separate trace module for the UAD2 Next. In our case, this is the parallel trace module. That module is plugged into the UAD2 Next, and then you need to connect to the target board via a separate trace adapter that is shown here. This is one possible configuration. So you have the debug adapter connected. This is the standard one, which is also used with the UAD2 Pro. You can connect directly to the trace adapter, and the trace information and the debug information are handled by one interface, which is a standard CoreSight 20-pin interface on the board. And to use the trace pins on the board, you need to enable them. The reason for that is that the trace pins are usually shared with some GPIO pins and should not be enabled by default by the debug tool, and that's why we have the enable sequence disabled in the default target configuration. You can enable them very easily. I show you this later on how it works. Okay, then have a look at the real picture. That is what I have on my desk right now. So you see the UAD2 Next connected using USB to my PC. I have a slightly different setup of the adapters and the connectors here. So we have separate connectors on the board for the JTAG and the SWD. I have zoomed in a little bit here and changed the perspective. So that is the target adapter or the debug adapter here connected to the interface on the board, and then we have an micro connector, 38 pins for the trace adapter here, and the debug adapter and the trace adapter is separated in that case. You see also the trace module here, which is plugged into the UDE to next. And what else? Okay, just uh, for your information, UDE to next can also be connected using Ethernet to the debugger, so you can also do some remote debugging. So, okay, let's jump to the debugger again, and I'd like to show you how tracing is working with UDE for the S32K. I have prepared a workspace for that, which basically uses the same target application. So if I press OK, then I can verify the flash memory contents, and we see there's no differences here. Close it, and then we can start the application. So I'd like to show you at first tracing into the ETB, the on-chip trace buffer, and then tracing via the external trace interface into the UAD2 next. In the first example, we want to trace a small piece of code which is running on Core 2, which is a clock. Let's enable this breakpoint, and here we are right now at the beginning of a periodically executed clock function. It is calling update seconds, and from that we do a updates minutes after a minute is up, and the same applies for the when the hours are up. So we get here this update hours function. We want to test this function here by a simple test case. I want to see the wraparound when the minutes are up, and for that I use tracing also to get the code coverage. So at first we need to, of course, write the test value. I can change the seconds value here. And then we need to configure the trace. That's quite simple. I want to trace across all the clock functions. So the best way to do that is to end the trace here at this line. I can click right, configure trace, trace to here. We can also have a look at the trace configuration. So on the Core 2 trace client, we have here the code trace enabled. We have also timestamping, but for the code coverage, it's not necessary. What we need to change is the synchronization period. The reason for that is the trace memory we are using, the ETB, has only 4K, and synchronization messages are now issued every 16K, which is quite too long to get the synchronization messages that we need to decode the tracing. So I reduce the period here to 256 bytes. Then we can look at the general tab. Here we have the so-called capture device, which is the ETB, and 4K are available. Pressing OK, and then we can start the trace recording, pressing that button here, and then we can execute our code. Trace has been recorded. So you see also in the trace window, we have the colors of the cores. So this indicates we are having a trace of core 2. And then we can open the trace analysis windows, for example, the code coverage, start the analysis of that, look into our achieved code coverage, which is not good at the moment. So that is because we have only one test case here. So everything is in yellow. That means only we have not achieved 100% coverage. We can also look at the executed functions in a more convenient way using the execution sequence chart. I open that and we start the analysis, and we get, after a few seconds, the graphical representation of the executed functions over time. At the very beginning, there's nothing happen which are very interesting, but at the end we have the execution of our clock functions here. You see, we have not a very long trace here. That's because we have only a limited amount of trace memory available. And to do a more detailed timing analysis or something like that, it makes sense to switch to the external trace interface and store the trace information into the UID device. For example, in our UID to Next, we have up to 512 megabyte available. And I told you before, to use the external trace memory and the external trace memory, we have to configure the pins that are shared with the GPIO so that they are used for tracing. I have already prepared that, and I show you. We have to switch to Core 0 and go to the target interface configuration. And here we have at the Connect tab the initialization commands that I have shown you on the slides before. I have already changed the default setting. By default, the initialization commands for the standard pins for trace are disabled. I have enabled them by removing the commands here. Okay, and then if you have changed that, you need to reset the target by, for example, connect them, or pressing the reset button or something like that. Okay, to show you the external trace, I go now to the Core 1, where we have a scheduler implemented that is running there. So we have some task functions here which are executed periodically. And we want to start the trace from this Core 1 worker function. I can again use right-click, configure trace, and we want to start the trace when the Core 1 worker function is executed. And then in this case, we need to go again to the trace configuration, go to the general tab, and then we can change the capture device. UID to Next parallel trace means we want to use the external trace interface for doing the tracing. And we select 4 megabyte for the trace memory. We can now have a look at the Core 1 trace setup. And here it is important to do a timing analysis, of course, to have timestamps available. Because of the 4-bit trace interface that we have here, we have a limited bandwidth. And with that setting here, we definitely will get some overflows in the internal FIFOs of our trace system on the S32K. For that reason, I reduce this value, for example, to every 16 clock cycles. Then I press OK. Then we start the application, start the trace. Trace has been stopped automatically because the trace memory is completely filled. And then we can open the execution sequence chart again, start the analysis, and then we can also look at some profilings. This is basically in the core graph. Select the core 1, start also the core graph analysis and also the analysis providing us some profiling information. So let's jump back to the execution sequence chart. We can unfold this, zoom to the complete range, and then also show some labels here, and we see the execution of our simple scheduler here and also the timing behavior of that. Okay, this ends the webinar for today. If you have any questions, then please use the webinar panel or write us an email. All the webinars we did together with Hitex are recorded, and the video recordings will be available on the Hitex YouTube channel, and also we provide links at the PLS website. Thank you very much for your attention.